In this skill, we're looking at questions to do with thermal equilibrium. So what that means is that we're going to be mixing together two things that have different properties, and they're going to come to a thermal equilibrium, which means they're going to end up with the same temperature as each other. And the whole basis of this idea is that the energy released by one of our substances is going to be equal to the energy absorbed by our other substance. So it's a transfer of energy between two substances. And the amount given away by one is always going to equal the amount accepted by the other. So let's go ahead and look at this question. Here we've got two different substances. Sample 1 is water. It has a mass of 100 grams and initial temperature of 30 degrees C. Sample 2 is aluminium. It has a mass of 100 grams and a temperature of 70 degrees C. We're also told that liquid water has a specific heat capacity of 4.19 joules per gram degree C, and solid aluminium has a specific heat capacity of 1.18 joules per gram degree C. Let's add that information onto our diagram so we can visualize it more easily. First, let's compare our information for each of our samples. So the first question asks us to compare the temperature. Which has a higher initial temperature? We can easily see sample 2 has a higher temperature. It's at 70 degrees C versus 30 degrees C for sample 1. What about mass? Both of our samples have 100 grams as their mass, so they have equal masses. Lastly, the heat capacity, that's C, that's our specific heat capacity. We can see water has a specific heat capacity of 4.19, which is greater than that of aluminium, which is 1.18. So sample 1 has the higher heat capacity. Okay, next we're told the student pours both samples into a polystyrene cup calorimeter. That's shown here. It's a polystyrene cup with a polystyrene lid with a thermometer sticking through it. The idea with a calorimeter is that it's thermally insulated, so it doesn't allow heat to enter or escape through its walls. So that means whatever heat we put in when we add our substances and close the lid, that total heat should stay the same inside our cup. It's like a closed system. We then wait for the mixture to reach thermal equilibrium. So what that means is that our cooler sample is going to increase in temperature and our warmer sample is going to decrease in temperature until they have the same temperature as each other. That's what thermal equilibrium means. So in this question, sample 1 is only 30 degrees C, that's cooler. Sample 2 is 70 degrees C, that's warmer. So the cooler sample, sample 1, is going to warm up. And the warmer sample, sample 2, is going to cool down until they have the same temperature as each other. And when sample 1 is warming up, it must be absorbing energy. So there's going to be energy absorbed by sample 1. And when sample 2 cools down, it's going to release energy. So there's going to be energy released by sample 2. And because this is all happening in this polystyrene cup calorimeter, which doesn't allow heat to enter or leave, so the energy absorbed by sample 1 is going to equal the energy released by sample 2. So we can fill in our next two questions here. Which sample gained heat and which sample lost heat? We know that the water gained heat, that was sample 1, and the aluminium lost heat, that was sample 2. Finally, we're asked, what is the final temperature of the mixture? Okay, so let's draw a little number line here. So we have sample 1, which starts out at 30 degrees C, and we have sample 2, which starts out at 70 degrees C. Now, right between those two, halfway between, is 50 degrees C. So the question is, once that mixture of the two samples has reached thermal equilibrium, is it going to be at 30 degrees C, 50 degrees C, 70 degrees C, or somewhere between? Here's our specific heat equation. That's the energy needed for a substance to change temperature by a certain amount. Q equals mc delta T. And we know that our energy absorbed is equal to our energy released. So we know that our M1 times C1 times delta T1 has got to be equal to M2 times C2 times delta T2. I'm going to move this down here so we can see it better. So first, let's imagine a situation where we have equal masses and equal specific heat capacities. So that would mean we'd have the same substance and the same amount for sample 1 and sample 2. So in that case, our M1 and our M2 would be the same. So if M1 is the same as M2, they would cancel out. If C1 is the same as C2, they would cancel out. And that would mean that our change in the temperature of substance 1 would be equal to the change in temperature of substance 2. That would mean our final temperature would be right in the middle. It would be 50 degrees C in this example, because that would mean sample 1 had gained 20 degrees C, sample 2 had lost 20 degrees C. The change would be the same for both. What about an example where the masses are different, but the specific heat capacity is the same? So if our specific heat capacity is the same, that would cancel out. But let's say we have a much bigger mass 2 than mass 1. Let's say mass 2 is big and mass 1 is small. Now, in order for the left-hand side and the right-hand side of our equation to equal each other, mass 1 times the change in temperature of 1 must equal mass 2 times the change in temperature 2. So that means if we have a really small mass 1, we're going to need a big change in temperature, so that when on the right-hand side we have a big mass, that can multiply by a small change in temperature, and small times big is going to balance out with big times small, so they can be equal. So in this case, if we had a really big mass of sample 2, that means our change in temperature for sample 1 would have to be bigger. So that means our change in temperature would be bigger for sample 1, and it would be smaller for sample 2. That would put our temperature, for our final temperature, somewhere between 50 and 70 degrees C. It would be closer to sample 2 than to the center point. Finally, let's look at this specific example. In this example, our masses are the same, so those are going to cancel out, but the specific heat capacity of sample 1 is bigger than that of sample 2. So C1 is big in comparison with C2 being small. So what that means, in order for our left-hand side and our right-hand side of our equation to be equal, that means our change in temperature 1 must be small and our change in temperature 2 must be big, so that when we multiply big by small, it's going to equal small times big. So what that tells us is that our change in temperature 1, so for substance 1, our change in temperature is going to be smaller than our change in temperature for substance 2. So on our diagram, that's going to look like this. This is our change in temperature 1, and this is our change in temperature 2. So we can see the change in temperature 2 is much bigger than the change in temperature 1. That puts our final temperature, I'm going to call it TF, somewhere between 30 degrees C and 50 degrees C. So let's fill in our answer here now. It's between 30 degrees C and 50 degrees C. So most of this question is straightforward. We're just comparing our two samples, deciding which one gained or lost heat. The way we decide that is based on the temperature. The one with the lower temperature will gain energy. The one with the higher temperature will lose energy. For the final question, we have to think about the energy absorbed by one being equal to the energy released by the other. We have to think about our specific heat equation and how each of our factors, including the mass and specific heat capacity, are going to affect the change in temperature for each of our substances. If the mass and specific heat capacity are the same for both samples, the change in temperature will be the same for both samples, and the final temperature will be right in the middle. If our mass is different or our specific heat capacity is different, the final temperature is going to be closer to the sample that had the bigger mass or bigger specific heat capacity, because that one is going to have the smaller temperature change in order for the energy absorbed to equal the energy released.